All right, we know that derivatives of inverse trig functions, let's put them to use. Okay, so derivative here, f prime of x. Okay, this is a three-stage chain. Isn't that fun? So let's see, so derivative of arcsine is 1 over the square root of 1 minus x squared, which would just be sine x, right? So take square root of sine, square it, fine. And then now I need to multiply by the derivative of square root of sine, which would be 1/2, and then keep the sine alone, and then to the power of negative 1/2, and then finally multiply by the derivative of sine, cosine. Okay, so I have arcsine. Arcsine as one stage, square root as the next stage, and then sine as the third stage. Okay. Next one, as I look at it, this is a fun product rule with several chains in it. Okay, so this is my first function. This is my second function. Okay, and so I need to do the product rule, which says to me, I remember that as 1, so I keep the first one alone, e to the 2t, and then multiply by the derivative of the second, which is multiply by 1/2, and then leave the inside thing alone to the power of negative 1/2, and then I need to multiply that by now the derivative of the inside, which is going to be negative e, or negative e to the 4t, so derivative e to the x is e to the x, times the derivative of the exponent. Oh man, okay, so that was fun. But I'm not done because I have to do the other part of the product rule, so I should now do the second square root of 1 plus e, 1 minus e to the 4t times derivative of arc cosine. Okay, so this is where things come into play. So I have negative 1 over square root of 1 minus e to the 2t all squared. And if you want to simplify that, you sure can. Then multiply by the derivative of the inside, e to the 2t times 2. Okay. All right. And if you want to simplify that, you sure can. I'm just going to leave it as a garbled mess. Okay. Last one. I am going to actually say this is on you to do. Okay. Be careful. I mean, confirm with like Wolfram Alpha, Photomath, or any of those other apps, right? You can just say, here's your derivative, or here's a function, differentiate. And keep in mind that there is, after you deal with arctangent, right, you have you have a chain rule, and then inside the chain rule, you actually have a quotient rule. So it's even more fun. So just be careful with that. Okay. Next example, we can embed these these inverse trig functions in with implicit differentiation. So let's see if we can handle all that at once. Okay, so we have to find y prime. We need to take this whole thing and apply the derivative with it. Okay, so on the left hand side, 1 over 1 plus x squared, which would be x y all squared, times, and then the derivative of the inside, which would be a product rule, so 1d2, right? So 1 d2 y prime plus 2 d1, which is just 1, is equal to, and then here we have a product rule again. Let's see, we have 1 d2 plus 2 d1. Okay, and now we need to go through the fun of simplifying all this. Okay, we can do it. We are good with algebra. Okay, so let's see, algebra-wise, we would need to, there's much different ways we can do this. I think the easiest way is just going to say, let's clear the denominator. So we have xy prime plus y is equal to, and then I'd have 1 plus x squared y squared times x squared y prime plus 2xy. Okay, and then I need to FOIL this out. So on the right side, I actually end up with, let's see, x squared y prime plus 2xy plus x to the fourth y squared y prime plus, what do I get? 2x cubed y cubed. Okay, so xy prime plus y prime. Okay, plus y. Okay, now rearranging, I'm going to keep the y primes on the left side. So I'd have x, move, let's see, these first, that term and that term over. So I'd have plus, minus x squared minus x to the fourth y squared is equal to 2xy plus 2x cubed y cubed minus y. Okay, and then at long last, I can say that y prime is equal to, let's see, numerator is 2xy plus 2x cubed y cubed minus y all over x minus x squared minus x to the fourth y squared. And that is a lot of x's and y's. Okay. I'm sure there's other ways that you could have got that. If you don't want to clear the denominator, you could certainly work with that denominator and then you'd maybe have more complex fractions. Okay. So that's another way to think about this. Last examples that we're going to work on are more just thinking about limits. Okay. Now this, I don't have a real good way of showing work necessarily on all of these. So we might just need to say, okay, well, we're going to reason through it as we talk through it. Otherwise, sometimes a graph might help. So in thinking about arcsine, right, we're curious about what is happening as we approach -1 from the right-hand side. And we can certainly back up and say, okay, well, you know, this is our arcsine function and we're approaching -1/2 from the left hand or from the right hand side. Okay, it should be getting closer to, well, let's see. So we have to switch inputs and outputs, right? But what are we getting close to as we get closer to -1 on the right side? Well, probably minus pi over 2 if we had a good graph, right? Again, we'd have to kind of view the y-axis as x and the x-axis as y. So this picture isn't the greatest. But with a better picture, we should be able to say from the graph, arcsine is going to approach -pi over 2 in this case. Okay. So now, next one, limit as x approaches 0 from the right of arctangent of natural log of x. Okay. So here's kind of my thinking. Okay. I'm thinking as x goes to 0 from the right, natural log, because that's where the x would go into first, right? Natural log of x is going to -infinity, right? Okay, so then what I'm thinking is as x goes to -infinity, what is happening to arctangent of x, right? As arctangent goes to -infinity, arctangent is going to minus pi over 2, okay? So that should be my answer. Okay. Another thing we can do with limits, and you might remember this, but limit of composite functions, right? We can actually move the limit inside. So we can actually say this is equal to the limit. Just kidding. This is equal to, I'll do equal to arctangent of the limit as x goes to 0 from the right of natural log of x. Okay. Composition of continuous functions is continuous. And so here this would be arctangent. I am going to use very bad notation. I'm going to say arctangent in quotes of -infinity. This is more in concept, right? And then you end up with that being equal to -pi over 2. Okay? So there's one idea. Okay? All right, our last example of our long video on examples. Okay, limit as x goes to infinity of arc cosine of this. Okay, what I'm going to do is I'm going to call all of this y. Okay, so I know y is equal to that. If I do cosine of y, that is equal to 1 plus x squared over 1 plus 2x squared, right? Just do the inverse function and then of all that. And so sometimes this approach can help you just to get rid of the inverse trig function, just to look at the rational function. That could help you because if you look at this, right, you can recognize from our previous study with limits that this is actually maybe approaching 1/2, right? So then you're thinking, okay, if you have cosine of some angle, right, what is that angle so that you get 1/2? Well, there's, I mean, of course, two different angles, but at least with that's the angle that's within the right restriction for cosine, that angle would have to be pi over 3. Okay, so then you're thinking that this would be pi over 3. Okay, now how do you show that more formally, right? What we could do is sort of do this idea that we did over here and pass that limit into the interior of arc cosine and say this is arc cosine of the limit as x goes to infinity of 1 plus x squared over 1 plus 2x squared. And then we could do, we could multiply by everything by 1 over x squared to numerator and denominator. And then I get arc cosine of limit as x goes to infinity of 1 over x squared plus 1 over x squared plus 2, and then lo and behold, I get arc cosine of, arc cosine of 1/2, which is pi over 3. Okay, so long way to get to the answer that I already kind of knew, right? But this is the more formal approach. All right. So lots of things to consider, lots of things to keep track of, but at the end of the day, right, we just have to remember our arc or our inverse trig functions, and then as we saw earlier, lots and lots of chain rules. Okay, so be on the lookout for those.